So should we just dive into day 19? Let me just get a marker here for my benefit and see what 19 is all about. Medicine for Rudolph. Rudolph the red-nosed reindeer is sick. His nose isn't shining brightly and he needs medicine. He needs custom-made medicine? Okay. What are we doing? A simpler machine that supports only the following replacements. What am I doing here? So what are they looking for? How many distinct molecules can be created after all the different ways you can do one replacement on a medicine molecule? All right, well, let's see what the input looks like, because I'm still confused as to what this is looking for. Get input 2015-19. Okay. So we have a bunch of atoms on the left, and I guess the replacement for them on the right. And at the end of the file here, we have a giant molecule, which looks like it contains some of this stuff here. I'm seeing a lot of them end in AR. I don't know if that's important. E is OMG. That's funny. Okay. So we're trying to see how many distinct molecules can be created after all the different ways you can do one replacement on the medicine molecule. So basically we're looking to count all of these guys inside the molecule. Okay, this seems like, okay. It doesn't seem too bad, right? Let's create 19 here. Let's create 19 here. Let's create 19 here. Let's add 19 to this. Let's fail to build. Grab the file name and 15, 19. There we go. So I guess the first thing is just parsing the input. We can grab these mappings, but my brain first went to doing a hash map, but the hash map's wrong because we have multiple things on the left mapping to things on the right. So we can either do like a hash map with a vector on the right, or we could just do the reverse mapping. Since all we're trying to do is how many distinct molecules can be created after all the ways you can do one replacement, we can look for what the replacements are and just count those up, right? We don't need to do anything fancier than that. We don't care what they get replaced with. We just want to count how many times we can do a replacement. I don't know, maybe part 2 will be harder, but so let's see. Let's do this. For line in AOC lib, read lines, input day 2015 19.text. We're going to split on the arrow, right? Oh, first we have to see if we have a blank line. We're going to stop, right? If I remember correctly, that had, yeah, there's a blank line. So we stop at a blank line, and the next thing is the molecule. Kafka says, look at the example again. Okay. Given replacements above starting with HOH, the following molecules can be generated. So we can do HOOH, going from H to HO. We can go HOHO using the same thing, right? And then OHOH. And then, or we could get HHHH using this. Kafka says it matters what you replace and what you replace it with. Right. So if I have a mapping that goes this way, I can look. Well, let me code what I'm thinking, and then maybe we can see where where the bug lies. Because I think all we need to do here is if line. Oh, this is bad. I just remembered. I strip out blank lines here. So we can just look for the first line that doesn't have an arrow. So if let sum left right is equal to line dot split once this, right? And now left and right are strings. If we have a none, then we have the molecule. So we actually have to put the molecule in here, right? Molecule is a string, and then the mapping. Let's just call them combinations. Hash map. And that's just a string to a string, right? Although we had problems with that before because of we had to do a bunch of cloning to get that to work. I think it was day 12. That was just really annoying. Let mut combos hash map new. No, we don't have to do that anymore. So this is just self combos insert left clone, right clone, and then otherwise self molecule is equal to line to string. And then here, let's just print all of the combinations, self combos, and the molecule, so we can just see what we have. Oh, I put a comma there. That's not good. And then here I have to say use. I gotta figure out if there's a way in NeoVim I could just have it insert the use statements on its own, and then combos. Oh, toString. Can we do it that way? Abzado, thank you for the follow. Okay, so this doesn't look like enough. Oh, right, because that's right. I wanted to do it the other way around. Right to left. There we go. That looks better, right? There's more of them now. Dusty Posy says, what's running in the second terminal? This is called Bacon. A watcher. Yeah, it's a watcher. It's a special watcher called Bacon, which you can just say, you know, cargo install Bacon, which was in my history somewhere. There it is. And Bacon will just run whatever you ask it to run. You hit question mark and it shows you the different options here that you can do. I can do a check all job, a Clippy job, whatever the default job is. You can open docs if you have docs on there. Or you can hit T and it'll run all the tests. It's just convenient to have it sitting here running. And then you can turn on and off line wrapping. So it's a neat little program. It's on GitHub, open source, so it's like a step up from just using Cargo Watch. It could be better. There's a bunch of improvements that could be made to it, but it's good. All right. So we have the mappings. So now the question is, what can we replace? And it says how many distinct molecules can be created after all the different ways you can do one replacement. So I need to do a replacement, replace it with the thing that I'm replacing it with. I need to find this, replace it with an H, and then add it to a list of distinct molecules. Okay, that could be a hash set. Dusty Posy says, if it's open source, that's something we could do on stream. Yeah, we just need to think of a good feature to add that wouldn't take forever to figure out how to do. That's all. One feature I would like is, like in the testing, it runs all the tests. I'd like to be able to pop up a little window and say, okay, just run like these tests, right? Do a search for that and just run those tests. Right now it runs all of them, so you have to kind of page your way through looking for the test that you're interested in. Although, you know, just seeing that they're all okay is fine, because I mean, that's all you need to see is, you know, if all the tests pass, that's fine. But just running a subset would be obviously faster if you have some slow tests. So I think that would be a convenient thing to do. Oh, let's go back to run and wrap. All right, so for part one then, what we can do is we can loop over all the combinations we have. If I do that, what is key and val? Those are strings. I don't want to consume it. Yeah, okay, so there we go. So now, is there a way in Rust that we can figure out Rust string match list? Where's the doc. I just want the string doc. There we go. So what do we have over here? Is there a find? Maybe there's a find in stir. Are match indices. So is there match indices? An iterator of disjoint matches of a pattern within this string slice, as well as the index that match starts at. What does it return? Oh, it returns tuples. I don't need the tuple though. I just need the. Oh, and this just returns the matches. I guess we could ignore the tuple then, right? I mean, the second half of the tuple. All I need to do is know the location, because what I want to do is strip the molecule, split the molecule at that point, and then strip out, right? So I want to say, like, in self molecule match in DICES on key val. So I want to look for val and replace it with key, right? Because I flip these guys around. Yeah, so I want to look for the P and replace it with PTI. I want to look for H and replace it with whatever the heck that is. So, right, so we'll say val here, and then that should give us a tuple of usize and stir. Then we can split at m.0. Right, m.0 is our usize. And now left and right are the strings that make up the left side and the right side. We need to, let's do this. Print ln molecule self molecule, and then I can print the left and right. Splits to left and right. And that way we can take a look at what we're getting. Kafka says, wait, I'm on that problem in 2015. So you're doing this one right now? Oh, I forgot to put break. Put a break here so we don't do them all. Where's my splits? Where's my word splits here? Oh, I want to just return. Return create output. Oops. There we go. There we go. And here it is, splits 2. So what we're doing, we found something. So CR and SIRN. So we must have found, here, I should put print where it goes. Kafka said, well, I stopped for a bit. This is where I stopped. Haven't worked on it since February or so. Oh, okay. Yeah, so so if you stopped here, this probably means this is going to be a toughie, right? But let's see. Let's see what we got. And what did we split on? Println val, right? B. Oh, now it came up with a different one to split on. Okay, so here's the B, right? So we have this left half and then we have the right half because we split on B. So that means our right side has to be replaced with key. Let's put a plus sign there. But we want to actually strip the B off, right? All right, so we replaced CA with this, and we want to remove this CA. Okay. So that would be right dot something. Is there a split? Split at. Split and. Can I just split a section and get like the end of the string? What does split off do? Splits the string into 2 at the given byte index. Returns a newly allocated string. Self contains bytes 0 to at, and the return string contains bytes at len. Oh. Oh, so that modifies the string. But we can just allocate it and do it all in one go, right? We can say let right is equal to right.toString, because this is a stir. So we can allocate a brand new string. And then we can split it and free it and say split off. What are we going to split off by? The length of the thing we found. Right, and we could just use shadowing to get that to work. Okay, B splits. Okay, and yes, we split off the B. There's no B at the front now, but did we split enough? Here it is. All right, TH, PB, CA, CA. Yes, okay, so that was good, right? Because it's CA, calcium, 2 calciums. We removed the boron and we inserted that thing. And now what we want to do is save it, right? So we want to actually have a hash set. And so we create here, let mod a hash set is equal to hash set new. And then what we're going to do is insert, instead of the print lines here, we're going to say hs.insert format bang left key right. Right, and that creates a unique one, and that way if we generate one that's identical to another one, the hash set will fold that for us. And all we care about then is how many are in the hash set, right? Let me take a look again. How many distinct molecules can be created after all the different ways you can do one replacement on the medicine molecule? So we're going to go through each one of the combos once, right? We're going to find all the locations where we can match that particular combo. And then we do a single replacement. and insert it into our counter. Okay, I think that's the right answer. Is it len or size? I guess it's, so I got 518. What'd you guys get? Yeah, there you go. That's the right answer. Okay. So that wasn't too bad. We're able to parse. I'm just concerned what's going to be part 2, right? Where do you go from here? All right, let's commit these changes. (2015) day 19, part 1. Dusty Posey says, "Congrats, thank you, thanks very much." All right, so part 2 is, now that the machine is calibrated, you're ready to begin molecule fabrication. Molecule fabrication always begins with just a single electron E, and applying replacements one at a time, just like the ones during calibration. For example, you have these replacements. If you like to make HOH, you start with E, transforms to O, O transforms to HH, and then H on the second H get HOH. So you could make HOH after 3 steps. Santa's favorite molecule, ho ho ho, can be made in 6 steps. Okay. How long will it take them to make the medicine? Given the available replacements in the medicine molecule in your input, what's the fewest number of steps to go from E to the medicine molecule? Kafka says part 2 is construct the medicine from an electron. Yeah, okay. So how do we do that? I mean, my first thought is you start with E and then you use a backtracking algorithm to work your way up to the molecule in question, but that seems like it would take forever, right? The molecule is huge. Yeah, look at this thing. I mean, figuring out, I mean, you have a stopping point, right? I mean, you have the length. If you ever go beyond the length, oh no, you can't even do that, right? Because don't some of them shrink? Oh no, none of them shrink. They always get bigger. Okay. So once you hit the length of the molecule, then you stop and say, okay, start backtracking. So E can be replaced with HF, and then H, you can, pick one of the replacements and then you just keep replacing the H. Oh no, you can't do that, right? Because the H gets replaced with this, and then we have carbon. No, there's no carbon. So that gets stuck there. Yeah, a lot of these end in AR. That's kind of interesting. I don't know if we should like analyze the replacements, or if we should just write backtracking just from the start, or if there's another way to go. Maybe we go in reverse, right? You look for this in here and then just replace it with this thing, right? Kind of like what we did already, but just keep going forever until it gets down to E. I don't know. This one's tough. We can try seeing how far we get, right? With just doing a backwards thing. So we can look for, we start with a molecule. Self molecule clone. I don't want to change the input, although there's no part 3, so that's fine. And then we want to say, we want to look for, maybe we just look for the vowel, the first vowel in there, and then just replace with a key, just like we're doing here. All right, for product in self combos values. Right, so we just look for each one of the if let sum position is equal to molecule find product. Let's work. This is a, oh, interesting. I thought combos values would just give us a string, but this is a weird thing. If we found a replacement, then we can just pull it out, maybe, and then just start again. So, well, let's try it. Println. No, let's println afterwards. Let's first we extract it the same way we extracted it up here. So I can just copy this, right? Except instead of M0, oops, it's pause, right? And then we split off the product len. Right, and then our new molecule. So let's do this. Println replacing. Oh, we have to figure out what we're replacing it with. Okay. So we can do key value again. Replacing val with key. And then I just say molecule is equal to format bang left key and right, just like that. And then I want to, do we keep going or start again? And then we want to loop until we haven't done any replacements. We have no more replacements. So let mut done equals true, and this is done equals false. And then so we loop while not done. Done equals true. That's annoying. Let's just do loop here. And then here we can just say if done break. Like that. Let's see what this does. Oh, I forgot to return a string. It's running. Did I hit? Am I doing an infinite loop now? I must be stuck in an infinite loop. Okay. Cargo run less. Oh, I forgot to print out the new molecule. But you figured that eventually it would stop. Oh, it's getting bigger. I got it backwards. I got it backwards. We want to find key. Like that. This is key val. There we go. All right, so let's take a look at this. There we go. Now is this going to stop? Uh-oh. Yeah, this is not stopping. Why not? You'd think that it would eventually run out of things to replace, right? If done break. Oh, then it's always false. Yeah, that was dumb. No, it's still taking, still running forever. And print out the molecule. I don't know why this is not stopping. I'm very confused. All right, let's run this and see what the molecules are looking like. So it is shrinking. Oh no, it's not shrinking. Am I forgetting to? Oh, that's why. I'm doing the self molecule thing instead of the actual molecule. All right, let's try again. Yeah, now it's getting smaller and smaller and smaller. Okay, good. Does it get all the way to E? It does. Okay, so if we do that, we just need to count how many times we do it, right? Is that how many steps? Fewest number of steps to go from E to the medicine molecule. So we just have to count that up. Count plus equals 1. Let me count equals 0. And then we just say create output count. And then we can come over here and then say bacon run. 200. That seems oddly round, but let's give it a shot. There you go. That's the right answer. Okay, so that wasn't too bad. I thought it was going to be harder for whatever reason. I don't know. Anyway, this is good. Cargo. We should run Clippy. I was going to do it here, but then I remembered Bacon does it for me. Okay. Git status. Git commit dash AM 2015 day 19 part 2. All right, git push.